Hello, and thank you for joining me today as we continue our discussions on chemical kinetics. And specifically today, we're going to talk about first order reactions. And so, different chemical reactions have what we call different orders, and that's all based on stoichiometry, which we're going to talk about here today. So, some reaction rates, when we talk about rate of reaction, so molar per second, depend only on one reactant, raised to the first power. And these are called first order reactions. So your rate law becomes the rate is equal to K, which is your rate constant, times the concentration of A, which is your one reactant. Okay, so we're going to look at these today. And so when we put K, we're talking about K and A in a first order reaction. So your rate is equal to K times concentration of A, which we talked about. Or in the first, like we talked about earlier, a rate is looking at a change in concentration divided by time, or a change in time. Okay, and so because both of these are equal to rate, we can solve them for rate. And so we can set it up as Ka, this first one, is equal to the second one, which is negative change in concentration of A divided by change in time. If we rearrange these, we can put the concentrations both on one side and K and T on the other. And so we can divide, so we end up with this kind of situation. This is how we end up at this equation. We have K times concentration of A equals negative change in A divided by your change in T. So we're going to get T off the bottom, and we're going to get the A's on the same side. So when we do that, we're going to multiply T and move the negative sign. So I'm going to take both sides times delta T times the negative delta T. And I'm going to divide both sides by concentration of A. Okay, that's going to get us to this point. We have delta concentration, or change in concentration A divided by your concentration A minus or equals a negative K delta T. Okay, and so from this point, we're going to take the natural log, we're going to integrate this, and we're going to raise everything to the natural log. So we're going to take the natural log of this side, and that's going to set us up for where we're going. And so we change change in concentration of A, we make this our new concentration, and we make your regular concentration A naught, which is our initial concentration. So what you're going to do is you're going to take the natural log of your current concentration divided by your initial concentration. So basically looking for a percentage. What percentage of my initial concentration do I have left? That's what this is doing. What you have left divided by what you started with is your percentage. So natural log of your percentage equals negative KT. And so with natural log, the natural log of concentration of A divided by concentration of A naught is the same as natural log of concentration of A minus natural log of concentration of A naught. And that's where we get this plus natural log concentration of A naught from. This can be written this way, and we can add this over to the other side. So you end up with the natural log of your current concentration equals negative KT plus the natural log of the initial concentration of A. This equation follows the same format as the equation of a line. So y equals mx plus b, this would be y equals m, which would be k, t, which would be x, plus natural log of your initial concentration, which is b. That's your y-intercept. That's going to be where we're at. That's our y-intercept on our graph. And so when we plot this, if we make a concentration of A, natural log of concentration of A, over time, we get a linear graph, which we're going to show here shortly, which is what you see here. So in this reaction, we have methyl isonitrile, which is CH3NC, being converted to acetonitrile, which is CH3CN. So this rearranges the atoms in this molecule, and that's what we're looking at. So we only have one reactant, and the stoichiometry is a 1-to-1, so that's going to be a first order. So because it's first order, my rate is going to be equal to K times my concentration of methyl isonitrile. And so we can look at this. If I just look at concentration changes, I'm going to get this nice sloped graph because it's changing. It's not the same rate the entire time. As you have less concentration of your reactant, your rate slows down. But if I take the natural log of this, here's my straight line until I run out of substance and I get to 0. There's a straight line from my initial down to 0. So these are the same points as far as time goes, but you notice the change here. So this is a curved line, this is a straight line. And that is your first order reaction. So you need to know that in a first order reaction, if I take the natural log of the concentration over time, I get a straight line. That's the bread and butter, that's the gist of this. Now if we're looking for K, if I want you to find K, so we can find your rate constant from your natural log of A over T. So we can find this rate constant. Remember, your integrated rate law was this. Natural log of A equals negative KT plus the natural log of A naught. And if we look at this, we're going to get this line. Remember, this is the same as Y equals mx plus b, where this is the y-intercept and m is my slope. So using my information here, this is K becomes my slope. And so that's where that all goes together. All right. So we're going to look at this, and we're going to look at half-life. And this is our little piece that we're going to have to calculate and find. So if we're looking at half-life, we've talked about this in regards to nuclear decay. Now we're talking reaction rates. So half-life is now the amount of time it takes for 1/2 of the reactant to be used up. Okay? And so in a first order reaction, we have the natural log of A equals negative KT plus natural log of A naught. If I want to find the half-life, if I'm looking for half-life, I know that that is when half of A naught is gone. So I can, instead of looking for this, I know what this concentration is going to be because it's half of my original. So I can take the natural log of A naught over 2. Concentration of A naught over 2 is going to be my half-life. That's half my concentration. And this is going to be the time for my half-life as well. So now if I'm solving this, I'm going to divide everything by the negative sign. I want a positive K value because that's what I'm trying to find. So if I divide everything by a negative, this becomes negative and this becomes negative. And I can add this to the other side now. So I get negative natural log of A naught over 2 plus I added this over the natural log of A naught equals KT, T to the 1/2. And when we do this situation, I can flip them around. So this can be natural log of A naught minus the natural log of A naught over 2, which is what we did here. And these A naughts are going to cancel out. So you're going to have concentration A naught over concentration A naught over 2. And so we're going to flip this over. So we're going to multiply by the reciprocal. So it's going to be the same thing as taking this times 2 over the concentration of A naught. And so these are going to cancel out. So I'm left with 2. So this is the natural log of 2 equals K times T to the 1/2, which is what we have here. And then I know that T to the 1/2 is the natural log of 2, or 0.693 divided by K. So I can use this equation, and then I can substitute and I can solve for what I'm looking for. And we'll practice this quite a bit. But that is where we're going to stop today. I look forward to working with you in class a little bit more, and when you come back, we'll talk about second order reactions.